Welcome everyone to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today we're diving into a really fascinating headline. Reasoning models don't always say what they think. Sounds a bit like a human condition, doesn't it?
It absolutely does. It's almost anthropomorphic in a way. It points to a potential disconnect between what a model is actually computing internally and what it's outputting as a result. Very interesting. Should we delve into the details?
Definitely. I think it highlights a fundamental flaw in relying solely on output as a measure of understanding. It's like assuming someone who gives the right answer in a test actually understands the underlying concepts. We've all been there, faking it till you make it, right? Maybe AI is just really good at faking it.
And that's what worries me. We're building these incredibly complex systems, and we're essentially judging them by their performance on specific tasks. But what if they're just clever mimics? What if they haven't actually grasped the underlying principles?
Exactly. This raises some profound questions about interpretability and oversight, especially as we move towards more autonomous AI systems. If we can't be sure that a model's stated reasoning reflects its actual reasoning, how can we trust its decisions, particularly in high-stakes scenarios?
Okay, so thinking about this from a deep learning perspective, it makes me wonder about the internal representations these models are forming. Are they truly capturing the semantic relationships and logical connections that we associate with reasoning? Or are they just learning statistical correlations in the training data? I've been following the scaling law research, and more data really just seems to translate into better performance. It still works. Is it really reasoning, though?
That's my big concern with the more data approach. You can throw all the data in the world at a system, but if it doesn't have the right architecture, the right structure to represent knowledge and perform reasoning, it's just going to learn increasingly complex patterns without actually understanding anything. Like memorizing the entire dictionary doesn't make you a poet.
I agree. It's like teaching a parrot to recite Shakespeare. Impressive, maybe, but it doesn't mean the parrot understands the nuances of Hamlet. I suspect that current deep learning is a bit like that. It's incredibly good at pattern recognition, but it lacks the ability to abstract, generalize, and reason in the way that humans do. We're not even accounting for spatiotemporal relationships.
And this ties into the need for better oversight, right? If the model isn't actually saying what it thinks, then simply monitoring its outputs isn't enough. We need to be able to peek inside the black box and understand the internal processes that are driving its decisions. Otherwise, it's like letting a toddler drive a car because they seem to be pressing the right buttons sometimes.
Well, with oversight, that's where the scaling laws come in. More complex models require more sophisticated oversight. So as the AI gets better, we'll also need to scale our tools of oversight too, right? Is that the right way to think about it?
I think the scaling laws are interesting, but I worry they're predicated on the assumption that the current approach to deep learning is the right path forward. What if we're scaling the wrong thing? What if the underlying architecture is fundamentally flawed and we're just making a bigger, more opaque version of the same problem?
Exactly. The oversight is brute force too. I think there's a risk of getting caught in a local optimum, where we optimize for performance within the limitations of the current paradigm, without ever questioning whether the paradigm itself is adequate for achieving true intelligence. Imagine trying to build a flying machine by just scaling up a bicycle forever. You need a different approach at some point.
This is where I think neuro-symbolic approaches become really interesting. They offer a way to combine the strengths of deep learning, its ability to learn complex patterns from data, with the explicit knowledge representation and reasoning capabilities of symbolic AI. The question is, how do we effectively bridge the gap between abstract symbols and actual neural processes? How do we create systems that can truly reason, not just react?
So, neuro-symbolic. I get the appeal of trying to combine the best of both worlds. But how do you avoid the pitfalls of both worlds too? I mean, symbolic AI struggled with scalability and dealing with noisy real-world data. Deep learning struggles with interpretability and reasoning. Are we just creating a Frankenstein's monster of AI limitations?
That's a valid concern. It's not just about bolting two systems together. It's about finding a way for them to truly integrate and leverage each other's strengths. I think the key lies in developing better mappings between symbolic representations and neural activations. We need to figure out how to encode knowledge and rules in a way that can be seamlessly processed by neural networks.
And that's where I think the spatiotemporal aspect comes in. Symbols don't exist in a vacuum. They're grounded in our experience of the world, which is inherently spatiotemporal. If we can find a way to encode spatial and temporal relationships into our symbolic representations, that might be a key to bridging the gap with neural networks. Think of common sense, for example.
That's a fantastic point, Donald. It's about giving the symbols context and grounding them in the real world. Perhaps we need to explore more sophisticated representations that go beyond simple vectors and matrices and can capture the rich, multi-dimensional nature of our experiences. I mean, think about how much better we are at understanding something when we can visualize it.
Okay, so let's dig into this reasoning idea a bit more. What does it even mean for an AI to reason? Is it just about following logical rules? Is it about making inferences from data? Or is it something more complex, like understanding cause and effect, or being able to imagine alternative scenarios? Deep learning is very good at correlation. Causation is a lot harder.
I think true reasoning involves the ability to manipulate abstract concepts, to combine them in novel ways, and to draw inferences that go beyond what's explicitly stated in the training data. It's about having a mental model of the world and being able to use that model to make predictions and solve problems. That's where I think symbolic reasoning has a real advantage.
And it's not just about manipulating concepts, it's about understanding the relationships between them, especially in terms of space and time. If I tell you that the cat is on the mat, you immediately have a mental image of the cat, the mat, and their spatial relationship. You can even imagine what would happen if the cat jumped off the mat. Current AI struggles with this type of intuitive understanding.
Absolutely. The ability to simulate different scenarios and predict their consequences is a key aspect of human reasoning, and that requires a level of understanding that goes beyond simply recognizing patterns in data. It requires a deeper understanding of the underlying causal mechanisms. So how do we get there? That's the million-dollar question.
Well, I still think scale is important. I mean, look at the progress we've made in natural language processing with transformers. These models are incredibly complex, and they're trained on massive amounts of data. And they're showing impressive capabilities in terms of language understanding and generation. Maybe with enough scale, we can eventually bridge the gap between correlation and causation. I'm still an optimist.
I'm not convinced that scale alone is the answer. I think we need to fundamentally rethink the architecture of our AI systems. We need to move away from purely data-driven approaches and towards more knowledge-based approaches that can explicitly represent and reason about the world. I think that's really the only way we will be able to achieve human-level intelligence. Maybe not even then.
I think it's a combination of both. Scale is important, but it needs to be coupled with a more sophisticated understanding of how intelligence works. We need to figure out how to encode spatiotemporal relationships into our AI systems, and we need to develop algorithms that can translate between different coordinate representations. Only then can we hope to achieve true reasoning.
So let's bring it back to the original headline. Reasoning models don't always say what they think. What are the practical implications of this? How does this affect our ability to trust and deploy AI systems in the real world? I mean, think about self-driving cars, medical diagnosis, financial modeling. These are all areas where we need to be able to rely on the reasoning of AI systems.
Well, in the short term, it means we need to be very careful about over-relying on AI systems, especially in high-stakes scenarios. We need to have human oversight and validation to ensure that the AI's decisions are sound and aligned with our values. And we need to be constantly monitoring these systems for biases and errors.
I agree. I think it also means that we need to be more transparent about the limitations of current AI systems. We need to be honest about the fact that these systems are not truly intelligent and that they can make mistakes, even if they seem very confident. We need to manage expectations and avoid hype.
And it means that we need to invest in research that goes beyond simply scaling up existing deep learning models. We need to explore new architectures, new algorithms, and new representations that can better capture the complexities of human reasoning. We need to be willing to challenge the prevailing orthodoxy and explore radical new ideas.
Okay, so let's talk about some concrete examples. Imagine an AI system that's used to make loan decisions. If the system is simply learning statistical correlations in the data, it might inadvertently discriminate against certain groups of people, even if it's not explicitly programmed to do so. It might be saying it's making a neutral decision, but its internal reasoning might be based on biased data.
Right, that's a classic example of algorithmic bias. And it's a reminder that AI systems are only as good as the data they're trained on. If the data reflects existing societal biases, the AI system will likely amplify those biases. This also shows why oversight, with a focus on scaling to match the AI, is important to catch these edge cases.
And it highlights the need for explainable AI. We need to be able to understand why an AI system is making a particular decision so we can identify and correct any biases or errors. If we can't peek inside the black box, we're essentially flying blind.
And it underscores the importance of considering the broader context in which AI systems are deployed. We need to think about the potential social, ethical, and economic consequences of these systems, and we need to ensure that they're used in a way that benefits all of humanity. The context is very important.
Another example, consider an AI system used for medical diagnosis. If the system is simply recognizing patterns in medical images, it might miss subtle cues that a human doctor would pick up on. It might be saying that a patient is healthy, but its internal reasoning might be based on incomplete or misleading information.
That's a scary thought. And it highlights the need for AI systems to be used as tools to augment human expertise, not replace it. A doctor can evaluate the AI's findings.
And it underscores the importance of incorporating domain knowledge into AI systems. We can't just rely on data-driven approaches. We need to encode medical knowledge and reasoning principles into these systems so they can make more informed decisions.
And it emphasizes the need for AI systems to be able to explain their reasoning to human doctors. If a doctor can understand why an AI system is making a particular diagnosis, they can better evaluate the system's recommendations and make their own informed judgment. It's like having a second opinion, but you need to understand where that opinion is coming from.
Okay, so let's shift gears and talk about future research directions. If we want to build AI systems that truly reason and that say what they think, what are the key areas that we need to focus on?
From my perspective, it's all about scale and efficiency. We need to continue scaling up deep learning models, but we also need to find ways to make them more efficient and interpretable. We need to develop new architectures that can learn from less data and that can explain their reasoning in a clear and concise way. We need to figure out how to train on synthetic data too.
I think we need to move beyond purely data-driven approaches and towards more knowledge-based approaches. We need to develop new methods for representing and reasoning about knowledge, and we need to find ways to integrate these methods with deep learning. We need better neuro-symbolic architectures.
I think we need to focus on encoding spatiotemporal relationships into our AI systems. We need to develop algorithms that can translate between different coordinate representations, and we need to find ways to ground our AI systems in the real world. How can we make our systems understand common sense, for example?
I agree with all of that. From my perspective, I'm particularly interested in exploring the connections between neuroscience and AI. I think we can learn a lot about how to build more intelligent machines by studying the human brain. How do our brains represent knowledge? How do we reason? How do we make decisions? And how can we translate those principles into AI systems?
I mean, the brain is the ultimate example of an intelligent system, but it's also incredibly complex and poorly understood. I wonder if we're really ready to start borrowing ideas from neuroscience. I mean, shouldn't we understand deep learning completely before we start getting more complicated?
I think we need to be open to all different approaches. And I think neuroscience can offer valuable insights into the design of AI systems, even if we don't fully understand the brain yet. It's about finding inspiration, not imitation. Look at how vision models were inspired by the visual cortex. That's pretty useful.
And I think it's crucial to remember that the brain is not just a passive receiver of information. It's an active agent that's constantly interacting with its environment. If we want to build truly intelligent machines, we need to give them the ability to explore, experiment, and learn from their experiences. The spatiotemporal experience of the world is crucial.
So, thinking about specific research directions, I'm intrigued by the potential for applying insights from neuroscience to improve the attention mechanisms in AI systems. The brain has incredibly sophisticated mechanisms for filtering information and focusing on what's relevant. Can we use those insights to design AI systems that can prioritize tasks and information in dynamic and complex environments? Scalable oversight is, after all, a question of focus.
That's interesting. I'm also curious about the potential for using spiking neural networks to build more robust and interpretable AI models. Spiking neural networks are more biologically realistic than traditional artificial neural networks, and they may offer a way to combine the power of complex interactions and pattern recognition with the conceptual clarity of symbolic representation.
I'm interested in exploring the potential for incorporating neuro-inspired principles of hierarchical organization and modularity into AI systems. The brain is organized into a hierarchy of interconnected modules, each of which performs a specific function. Can we use that model to build AI systems that are more scalable, flexible, and robust?
And I'm interested in exploring the potential for developing AI systems that can translate between different coordinate systems. How do different coordinate systems, for example, physical space, abstract concepts, temporal sequences interact in the decision-making processes of complex systems? If AGI is about translating between these different frameworks, we need a better understanding of these translation algorithms and how to design them.
Okay, so let's wrap things up. The headline "Reasoning models don't always say what they think" highlights a fundamental challenge in the field of AI. We need to move beyond simply building systems that can perform well on specific tasks and towards building systems that can truly reason, understand, and explain their decisions. And that requires a multifaceted approach that draws on insights from neuroscience, cognitive science, computer science, and philosophy.
I agree. It's a complex and challenging problem, but it's also incredibly exciting. The potential for AI to transform our world is enormous, but we need to be careful to ensure that these systems are aligned with our values and that they're used in a way that benefits all of humanity. Even if scaling is all we have, we should focus more on scaling our oversight.
Absolutely. I think it's crucial to approach AI development with a healthy dose of skepticism and humility. We need to be honest about the limitations of current AI systems, and we need to be willing to challenge the prevailing orthodoxy and explore radical new ideas. AI is powerful, but we need to know its limits.
And we need to remember that AI is not just about building intelligent machines. It's also about understanding ourselves. By studying AI, we can gain new insights into the nature of intelligence, consciousness, and what it means to be human. I think the real focus is on coordinate transformations.
Well said, everyone. Thanks for joining me on this fascinating exploration of AI reasoning. It's clear that there's still a long way to go, but the journey is definitely worth it. Until next time on Cognitive Spirals.